Hello and welcome to XR21. My name is Sebastian Hahner and I'll present a paper modeling data flow constraints for design time confidentiality analysis. Let's start with a short motivation. Data flow-based confidentiality analysis enables software architects to model data flows in design time and to identify confidentiality violations in architectural models. As shown here on the right side, a simplified example based on the travel planner case study where users try to get flight offers from a travel agency and then book those flights using their own credit card. An exemplary data flow would be here the user requesting flight offers from the travel agency, which forwards this call to the airline server, or the users then selecting one flight and booking this flight by using the credit card details, which then flow to the airline server directly. Here we try to find confidentiality violations using role-based access control and annotate this model using the roles user, travel agency and airline. An exemplary data flow constraint would then be that data is only allowed to flow to entities with authorized roles. And as an example, the sensitive credit card details are only allowed to flow to the user and the airline after the user explicitly allowed this on his smartphone using the Credit Card Center app. If the user does deny this flow or the data is, for example, transferred to the travel agency server, a data flow constraint violation would occur. And to perform such analysis, the architecture and the annotations are transformed to an underlying formalism. While data flows and their characteristics are annotations on the architectural model, constraints are described directly by using the analysis formalism. Here the problem arises that software architects have to leave the architectural domain and abstraction level. Our contribution is a domain-specific language on this architectural abstraction level, a mapping to the analysis formalism and the mapping of analysis results back in the architectural domain. The benefit of this approach is the reuse of non-terminology, which is easier to use and grants higher productivity. To go with the previously introduced example of the constraint, data is only allowed to flow to entities with authorized roles. Based on our DSL, this could look as follows. We define a constraint based on the annotations on the architectural model, the access rights and entity roles, and define a never flow constraint, so data with selected rights is never allowed to flow to nodes with selected roles, and this is especially the case if the intersection of rights and roles is empty, which then would raise a confidentiality violation due to a violation of the role-based access control model. Besides this exemplary concrete syntax, we also present the abstract syntax of our DSL, which is shown here on the left. We define constraints, for example, to enforce RBAC, which contain exactly one rule. If this rule does not hold, then a confidentiality violation occurs. Each rule contains at least one data selector and one destination selector. In our running example, the data is selected based on the access rights and the destination is selected based on the roles of the entities accessing the data. In our example, we used annotations of access rights and entity roles. And since these are dynamic values and not fixed, for example, the user is enabled to allow the airline to access his credit card details, but he could also deny it, we can use no fixed values but have to add a condition. This condition describes the dependency between different characteristics, for example, based on the data selectors and destination selectors. In our example, based on role-based access control, we define that the intersection of rights and roles is not allowed to be empty. Otherwise, this condition would be evaluated to true and a confidentiality violation would occur. In order to use this DSL, a mapping to the analysis formalism is required, which is compliant to the mapping of the architectural model. First, we define our data flow constraints which reference the architectural model, for example by referencing characteristics or annotations. The DSL mapping takes these constraints and transforms it to the analysis formalism, which also requires tracing information since we need to know the originating architectural model elements and their transformation results. These mapped constraints are then input to the analysis process as well as the mapped architectural model. Afterwards, the analysis results, namely the constraint violations, have to be mapped back to the architectural domain in order to ease the interpretation through software architects. Here we also need again the tracing information in order to get the originating elements from the architectural model. And last, we also need the original constraint definition in order to add more semantic information in the architectural abstraction. Last, the combined results are shown to the software architects. Here we want to highlight the domain border. Everything which is important to software architects is above this domain border. They start by creating and annotating the architectural model. Then they define the data flow constraints using our DSL and by referencing the architectural model. And after the analysis process took place, they receive the already transformed results in the architectural domain. In this example, a constraint violation occurs because data, namely the credit card details, flow from the user smartphone to the airline without the prior acceptance by the user, and this is, as we defined, a confidentiality violation. In this process, everything which is not important to the architects, namely the transformations and also the analysis process, remains hidden. In order to evaluate our approach, we consider the goals expressiveness, usability and correctness. Regarding expressiveness, we asked whether the available DSL concepts allow the versatile definition of data flow constraints. Here we consider different scenarios and their constraints, which we derive from case studies used in related work. And the answer is that the expressiveness is sufficient for most of the evaluated constraints. Regarding usability, we asked whether our DSL provides an abstraction over the underlying analysis formalism and whether the DSL hides complexity. Here we measured the effort of different change scenarios and also re-evaluated the domain border shown before. The answer is here that the DSL requires less effort and also hides accidental complexity by requiring no knowledge about the underlying analysis. Last, regarding correctness, we ask whether the mapping is correct and also whether the analysis results of the underlying analysis formalism when used directly in comparison to mapped DSL constraints are equivalent. Here we conducted a formal correctness proof and compared the analysis results with the result that our analysis reaches a recall of 100% while still maintaining a precision of 92%. We close with a short comparison of related work. Here we identified two categories. First, direct analysis, which used the architectural models directly without transformation and thus do also not consider the gap between architecture and analysis. Second, indirect analysis, which transform the architecture into a formalism in order to perform their analysis, but do not provide a generic solution for bridging this abstraction gap. Also, these papers do usually not report on the mapping of analysis results, which we consider to be an important problem in order to ease the interpretation by software architects. To conclude, we presented a domain-specific language to define data flow constraints in the abstraction level of the architectural domain, which bridges the gap between definition and analysis. We also presented a mapping to the analysis formalism and the mapping of the analysis results back in the architectural domain, both being compliant to existing architecture transformations. Together, they shall enhance the formulation capabilities and productivity of software architects. In future work, we aim to enhance our DSL expressiveness. Thank you.